because that was bad. Ah, hello.
Okay, well, welcome back. So I was going to do my joke about the COVID vaccine, but most of you won't get it for ages.
I'm getting it tomorrow.
Oh, I even get it as well.
That's in the first years. They took several minutes.
Is that?
I'm getting the vaccine tomorrow.
Right.
Oh my god. The worst bit is that I even kind of understand why you made that joke, because it's self-referential, isn't it? I hate that so much. I'm so angry, dude. Terrible.
Right. What we've seen in Matthew's wonderful interpreter there is really the beginnings of a programming language. You know, the reason we study lambda calculus now is really to see in a very pure form all the processes that go on inside a programming language and how to implement a language. And you know, if we had the alpha conversion up and running there, what you actually have is a fully functioning programming language, actually a fully functional programming language as well. So lambda calculus is a very simple, small language. It's designed to be simple and small. But in these slides, I want to show some of the things that it's capable of doing. We're going to build up some structures within lambda calculus to represent things like booleans and numbers and recursion and loops, which can pretty much be put together to write the kinds of programs that you're more used to writing, showing that lambda calculus has the power of a full language. So, you know, again, the reason we do this now is to understand what these things are. We're going to understand what a number actually is, at least according to lambda calculus. So we'll talk about these applications. Then if we have time, I want to talk a bit about the meta logic of lambda calculus. This is proving things about lambda calculus rather than doing things inside the system, you know, as we saw with the MU system earlier on. But yeah, let's work inside the system for now. So a simple starting point is to encode Boolean logic in lambda calculus. Yeah, we've all studied Boolean logic before, true, false, and or and not. So the language we've seen so far doesn't contain any of those terms. It only contains the grammar of lambda calculus, but we are able to construct those terms out of lambda expressions. So in particular, we can construct a model of true as the function, and remember how to read these from last week, right? True is going to be the function which takes x and y as arguments and returns x. So basically it takes two inputs and it returns the first one and it throws the second one away. Why is that a model of truth? We'll see how it works. It's not obvious why this should be representing truth. False, we're going to do something similar. We have a similar input-output structure, taking two arguments, but this time we return the second argument and throw away the first one. Actually, a bit of insight into why this might be useful. You know, imagine an if statement, okay? An if statement is going to take two things. You know, if something's true, you're going to do the first thing. If something's false, you're going to do the second thing. Yeah? You have if true, then do X, otherwise do Y. If you're happy to make those definitions, you can then construct the Boolean operators. You can construct and or and not on top of them. Okay, and again, if you take these things initially just as falling out of the sky, you will find that these will make Boolean logic work. Okay, so if you take, for example, let's do true and true. So this is an expression in lambda calculus. Now notice all the lambdas have disappeared now because we're working with these higher level symbols. But you could write this out longhand if you like. You could write out what that and actually is. Yeah, that's lambda xy that returns xy f, and all of that is being applied to true. So remember, true is xy that returns x. Okay, and if you grind through the beta reductions on this, you'll find that true and true does actually equal true. And we might have a go at doing that either with a pencil or with a lambda interpreter later on in the workshop today. So does this notation make sense to everyone? It's different from, you don't expect true and true to be written like that. Remember, in lambda calculus, the operator goes first because and is the function which takes two inputs and does this thing to them. So we write the function first and then we give it the two arguments. Okay. So similarly, in the workshop, you can try it out with an or. You can say things like or, true, false. We're going to do true or together with false, and the result of that should be true, and that will just drop out from these expressions. And this will scale up to the Boolean algebra that you already know and love. So here's a more complex Boolean expression. Here we've got three input values. We've got a negation, we've got an and an or, and you can see the correct Boolean truth value of this should propagate through. So here we're saying, we start off with not true, so this is going to be false. You're saying false or false is still false, yeah? And now you've got false and true, giving you false at the other end. I see asking for attendance codes. I'll just post that again. So this kind of stuff, you have to do it. You have to do this with a pencil to really understand how the encoding works. Now, this isn't the only way to represent Boolean logic in lambda calculus. It is one choice of a representation. Now, remember, this logic is all about having a symbol which represents something else. And in this case, Boolean logic is being represented, and we're using lambda calculus to do the representing.
I have a question. Are there a finite number of ways of representing Boolean logic within the lambda calculus? I don't think there should be.
Yeah.
If it's true and complete, if we just want to enumerate over an infinite number of representations, we find a representation for Boolean in a different system, and then we represent that in the lambda calculus, and then we represent the lambda calculus representing that other system in the other system, and we can just ad infinitum.
Yeah, a good way to prove that would be to show, can you represent the lambda calculus in lambda calculus, which you should be able to do because it can do anything. So once you can do that, you can then recurse it indefinitely and come up with a whole different ways of having Boolean logic embedded in every level of that. Yeah. That's not a detailed proof, but it sounds like a decent plan for proving it. Or you might try and prove it by considering other families of functions. Yeah, is there a way you can just add arbitrary extra variables into each of these expressions in a way that they don't affect the computation, but just get carried around? Yeah? That way you could encode any arbitrary string into each of the variables, and you'd have an infinite number of options to do that.
Yeah.
Okay. So lambda calculus starts looking nice now. We've abstracted away the symbols underneath. So in particular, there aren't any lambdas here anymore. The lambdas are inside these symbols. And you can create something that just behaves as Boolean logic coming out of it. So here's how we can take those same representations of truth and false and use them to form this if then else statement. So you don't actually need to define anything. You can just use the operators directly. You can just say true x, y, and this means if true, then x, otherwise y. What I've done on this slide, I like this notation where we actually define a combinator called q. So these lambda terms are often called combinators when you drop the lambda. So I like to define this q combinator, and it doesn't actually do anything, right? It takes bxy and it just returns bxy, where b is a boolean and x and y are the two outputs. So this is going to represent if b, then x, else y. Okay. So the reason I like to define this is because it just looks nicer to humans when it's written out. So for example, here we're saying if true, then C, else D. And so that is going to evaluate to C because the input is true, and so we get the first argument. So you could just have written that as true CD, but I think by putting the Q there, it makes it clear that this is being used as an if. It's Q for question. Yeah. Question whether this is true or false. See what you get at. You can mix combinators and other lambda expressions. That's okay. So here we're saying ask a question. This time we're saying if false, then C, otherwise return this lambda expression here. And because this is false, we're going to get the lambda expression coming out. And as before, you can build these things up. Here's I think this is the Boolean expression from the previous slide, which evaluated to false. Yeah. So here I've taken an arbitrary Boolean expression, all written out as combinators, and now it's got two inputs, C and D, and we've asked the question, and we're going to get D because the input is false, so it's going to pick the second of the two options. Okay. Question from Matthew.
Yeah, so writing the operators for the Boolean logic, is it prefix essentially like you would do in mathematical form? So like you have the and
Yeah,
start.
so instead of saying x and y, you're going to write and x, y. Yeah.
So it just works like it. Okay.
Yeah. Well, if you were going to write 3 plus 2, well, you've not
It
done
should be-
numbers yet.
yeah,
In a
it
minute,
should
you're
be
going to see
yeah.
some numbers, and we'll do plus 3, 2. Yeah.
Thank you.
And that just arises from the structure of lambda calculus. It arises from this notion of defining a function and then applying it to some arguments. Yeah. This, in terms of lambda grammar, this is an application. And remember, the grammar of application is you give the function and then you give the arguments. Okay. So was there a question from Gary a moment ago? Gary, did you have your hand up?
I did. Yeah, I did. But I think you answered it. It was the previous slide where I wondered if you could. You spoke about abstracting the lambda away, and that was really what I was going to ask around that. If you could start off and the and tt equals t, or do you always have to go back through to that base level of lambda xy dot x and whatnot? But I think you covered that in the following slide. As you mentioned, things were abstracted. So that was all.
So depending on if you implement this, if you build your own lambda interpreter, there's probably different ways of implementing this. One way would be to immediately rewrite this in terms of the underlying expressions, right? You can go and write out what that and symbol actually is, lambda xy dot xyf. You could write the whole thing out, and now you've got a regular lambda expression, and then you set your interpreter going, doing beta reduction to get the answer. You might consider writing a cleverer lambda interpreter. This would be pretty advanced, that actually keeps the things in combinator form. When you do these with a pencil, as a human, you will tend to do that. So in particular, these combinators are describing Boolean logic, and so for me to evaluate this, you know, I didn't write that out as a bunch of lambdas, right? I used the higher level laws of Boolean logic. I said this is not true, so it's false. This is false or false, which is false. False and true is false. And I worked out what the answer to that was without having to write everything in terms of lambdas. Yeah, because I kept the higher level symbols in my head, and I did the algebra with those higher level symbols.
Okay. And so I'm
Yeah,
assuming okay.
In a computer implementation, it would be much more common to translate it into the underlying lambdas and then push the button to make it go.
Okay. Yeah. Brilliant. Thank you.
Okay, so yeah, now we've got Boolean logic, we've got if then else. You know, what else do we need to make a working program language? You know, probably numbers is the next thing. So we're only going to do natural numbers here, but it should give you a pretty decent idea about how to make other kinds of numbers as well. If you remember back in computer architecture, we talked about how to construct these other types of numbers out of natural numbers. So again, this convention can look fairly arbitrary, as if it's just fallen out of the sky, but there's a reason for it. And let's define 0 as this thing. It's a function which takes 2 arguments and returns the second one. Now, where have we seen that before?
False.
Yeah, that's actually exactly the same as false. Now, lambda calculus in this form is untyped, so there's no way for us to tell, unless we keep track of it in our own human heads, there's no way for us to tell whether this is meant to be representing a 0 or the Boolean false. Okay, so there are typed versions of lambda calculus that come along later to keep track of that kind of thing. But yeah, let's use this to represent 0. And then S stands for successor, and Z is kind of representing 0, but not quite, because the whole expression really represents 0. So again, if you've been reading Gödel Bach, you should recognize this kind of notation. Like, you often write the number 3 as the successor of the successor of the successor of 0. So 1 is going to be a function which takes the same arguments. Every numeral takes the same 2 arguments. And this time it applies S to Z, and it applies it once. Okay. Number 2, take the same 2 arguments, and this time we apply the function twice. So you start with Z, you apply S to it, and then you apply S to it again. Okay. And number 3, you start with Z and apply S 3 times. And when you think about it, this is a nice definition of what numbers actually are. They're the operation of doing something several times. Okay, so the number 3 means do something, do it again, do it again. That's the meaning of the number 3. So you might prefer to write these, rather than S and Z, if you write them with F and X, for example. You know, X would be the input, F would be a function, could be any function, and you're going to take that input and you're going to iteratively apply F to it. So you might take X equals 1, and F might be the function times 2, and this would do 1 times 2 times 2 times 2, which would give you the number 8. But if you put a number on the front of anything, it means do that thing so many times. And if any of you are using the Vi or Vim editor, this is the origin of the keystroke convention. If you type 3W, that means go forward 3 words. So W is a function to move along by 1 word. When you type 3W, the number 3 is a function which takes 1 argument, it takes the function after it, and it iterates it 3 times. So if you were to write something like this, 3fx, this would mean apply the function f 3 times to the value x. So this would happen if you actually used a number. If you take the number 3 and actually apply it to something else, it will iterate it. Normally when we do arithmetic, we don't actually use the numbers. We only use the symbols for the numbers. If we want to do 2 plus 2 equals 4, we don't care what it's 2 of. We don't say it's 2 jumping up and downs plus another 2 jumping up and downs is 4 jumping up and down. We're usually more interested in this abstract concept that a number plus a number gives another number. So usually we're not actually going to evaluate the numbers. We're not actually going to plug anything into the S and Z. We're just going to keep everything in this form. And if we were to do 2 plus 2 in that notation, we'd end up with 4 in this notation, and that would be the answer. But ultimately, the number 4 is the function which takes 2 arguments and iterates one of them 4 times on the other. And that's the nature of 4ness, doing something 4 times. So once you have this representation, as we did with Boolean logic, we can then construct operators acting on the notation. So the simple one to do is to create the successor function. Okay, so if you've been reading GEB, in GEB he takes this as a fundamental grammar of the logic. So this SSS0 doesn't compile into anything else. That's just the raw grammar of Hofstadter's TNT system. But here, lambda calculus doesn't have S's and zeros. It only has the grammar of lambda calculus, and so we have to construct each of these things. We've constructed the number 0, and then we're going to construct this operator S, which acts on a number, and it acts to add 1 onto the number. And again, we can play around with this with a pencil or an interpreter in the workshop. I'm just going to show it to you for now. Here is a way of defining a successor function. So this is a function which takes 3 arguments, w, y, x, and it returns this thing. It's applying y to w, y, x, and it will turn out if you apply this to a number of your choice, then it will take you, for example, from the number 2 to the number 3 if you actually crank that out with a pencil or with an interpreter. So here's a simple example. Okay, here we're going to consider the successor of 0, and again for Hofstadter this is fundamental. It's defined in the grammar, but in lambda calculus we're constructing this out of other stuff. So here's the number 0. Remember we defined this? Yeah, it's the same as the false function. Takes 2 arguments, returns the second one. And we're going to apply the successor function to it. Not worth going through every step. But this is the input. This is going to be W coming in here and showing up there. So you now see where that W was. We've got the 0 function is sitting in here. And then if you crunch through this, you will end up with the function that takes 2 arguments and applies the first one to the second one, which is equal to the number 1. Okay, as in this definition up here. So in the workshop, let's try out a few of these. Try adding 1 to the number 3 and show that it takes you to the number 4. So the successor function only adds 1. We obviously like to create proper addition next, where we're going to add one number to another number. And we now have the ingredients to be able to do that, because remember, a number now is a function. It's a function which iterates something that many times. And let's say you have the number 4 and you want to add the number 5 to it. Yeah, what are we going to do to the number 4 5 times to compute the result? We've got 4 plus 5, right? We're going to do something to the number 4, and we're going to do it 5 times.
So you're going to take your 4 lambda, and then you're going to apply a successor combinator.
Yeah, so we want to say something like successor of successor of successor, successor of 4. That's it. So we want to apply the successor combinator 5 times, right? And how do we apply something 5 times? That's the number 5. The number 5 is the function which does something 5 times. So all we have to do then to define addition, so here's our addition combinator over here. It's very, very simple. It's addition then is the function which takes 2 numbers and it applies the first number to the successor function and to the second number. Okay? So this is pretty neat. This is a nice definition of arithmetic from those 2 very basic operations. It's from the nature of a number itself and from the successor function. So remember, we're always going to write things in this notation. This means 2 plus 3. Yeah, we're performing the function add, and it's got 2 arguments. One is the number 2, one is the number 3. So from the definition of this is going to become 2s3. And again, this looks like the kind of thing you would type out in Vim. Yeah. Then spell it all out in longhand, chug through the beta reductions, and you should end up with the successor of 4, which equals 5 in this case. So when you do this, when you write out the steps of those beta reductions, you can actually look at that object in 2 different ways. Okay, one way to look at it is a proof. This is very definitely proving that 2 plus 3 is actually 5. Because you've started with your definitions of the numbers, you've started with your rules, you've shown, ultimately you've shown a bunch of applications of syllogisms or sequence from the lambda calculus, and you've made an argument beginning with the definitions and bringing you to the conclusion. So if you accept all the definitions, you now have a proof that 2 plus 3 is in fact 5. But at the same time, you can also look at this as the evaluation of a program that is computing that value. This is looking at it as a temporal process that is evolving over time. At each moment in time, you're doing an evaluation. And you've started with a system in a state that is asking the question like this. And you've ended up in a state that is containing the answer. So this is another illustration of this general idea that proofs are programs. Remember we saw Gary's work last time, I think. That Gary was writing out these proofs in a manner that looked very much like an assembly language program, executing on an underlying state. So you can read this either way. Read it as a proof or a program, they're the same thing. Fionn.
I think you might have a floating bracket closing side on the first expression of 2 plus 3.
That's very possible. Here.
Just thought I'd point it out.
Yeah, thank you for that.
No worries.
Let me make a note of that. Slide 7. I'll get that fixed too. Yeah.
Thanks.
That's important because if you're going to take it home and do it with a pencil, it has to be.
Yeah. Yeah.
If we find any errors, do let me know. Thank you. Yeah.
No worries.
Good. Ooh, you guys are good today. All right, what shall we do next? Yeah, multiplication is traditional. We've done add 1, we've done addition, now we're going to do multiplication. And it turns out we can define it like this. So multiplication is the function which takes 3 inputs and does this to them. Yeah, try it out if you like. Here we're doing 2 times 2. It's the function which does multiplication with 2 and 2 for arguments. And yeah, roughly this is going to go around and do addition a bunch of times. Although you can see, actually, we're not calling the underlying addition operator. You see, this involved a successor function. It's interesting, we're not using the successor function here. And what's the reason for that? The multiplication is actually easier to express than addition in a way, because remember, a number is the act of doing something n times. If the number 4 means do something 4 times, so if you simply take two numbers and apply one of them directly to the other without any other messing about, just take the number 3 and apply it to the number 4. Yeah, you can just write 3, 4. And this is the function which does things 4 times, and you're just doing all of that 3 times. So you'll end up with a function that does things 12 times. So this is actually simpler to understand than addition, because you're just doing that number that many times. Gary.
Sorry, this is probably a silly question. On the, we've got x22. If it was, say, x 23 times 24, how would that be represented? How would that be not get confusing?
Yeah, I don't know. Choose a suitable syntactic sugar when you build an implementation of it. I don't know. Maybe spaces. Maybe you include some white space, something like that.
Okay. Yeah. Makes sense.
Yeah.
Okay. Yeah, understand.
Yeah. Again, at the level of lambda calculus itself, we just don't care because these things are all human constructions. That 22 isn't a thing. It's a shorthand for a massive lambda expression, and it's that expression that actually matters. Okay, good. So at this point, something very interesting has happened because we now have numbers, and we have addition, and we have multiplication. And if you remember back in our introduction when we talked about Gödel's theorem, yeah, Gödel's theorem applies to logics which have this power. It has a very definite cutoff. So, there are some logics that cannot do arithmetic, or maybe they can only do addition. And Gödel's theorem doesn't apply to those. You don't have all these issues about impossibility, inconsistency, incompleteness. When you cross this threshold, this is the precise threshold that is required for Gödel's theorem to kick in. It's when you've got natural numbers and addition and multiplication. Okay. So this now gives us a hint that we're out in the real world rather than in some little toy logical system. We're out in the big scary world where there are going to be things that we cannot prove. We do not know if they're true or false, or depending on your point of view, are neither true nor false. And that's just from addition and multiplication, right?
I have a question. So I always thought of multiplication as repeated addition. So it was interesting to be talking about how actually in this system multiplication is a little bit easier to represent. But when you actually look at what Gödel did, multiplication is actually really important to the idea of incompleteness, and you can define. I've read that you can define certain finite systems that can perform addition but are not incomplete. But how does that work? Because if you can repeat addition, surely you can multiply.
But you'd need to express the repetition of it. Yeah, if you had a logic that could do addition and was able to express that type of repetition, then it would be able to express multiplication. Yeah, so there must be some extra ingredient as well as addition. You've also got to have that notion of recursion, doing something again.
Yeah, being able to nest it. Yeah, that makes sense.
Yeah. Okay. Good. Okay, so now we can do arithmetic. Let's look at some other ideas then. To make your Space Invaders game, you're going to need some data structures. We're not going to look at every possible data structure. Let's take the simplest example of a data structure, which is just a pair, ordered pair, A and B. And I'm going to change my notation conventions on this slide. So here, pair is a single token. This isn't P operating on A, on I, on R. Pair is just written as a single thing. For some reason, when the books go into data structures, they tend to switch to this word-based notation. Maybe because this is where you start to see functions that appear in real languages like Lisp and so on, functional languages. So if you'll let me have that notation convention, maybe just for this slide, I think let's define a pair then as a function which takes 3 arguments, a, b, z, and it returns z, a, b. Okay, and as with all these things, you think why on earth should that work, and then you try it, and you'll see why when you actually do it. So, for example, we can create a particular pair. So here we're going to apply the pair function to 2 arguments, a and b, and this is going to construct a pair for us. Okay, so this is like your constructor in almost in an object-oriented language, or creating an instance of a struct, at least. It's taken the 2 inputs and it's put them into this form that makes a pair. And then for a data structure to do anything useful, you need some algorithms operating on it. And the obvious things for a pair is a function to extract the first element and another function to extract the second element. And in this case, we already have these handy little functions for extracting first and second elements. If you remember, we called them true and false. So this is a horrible overloading of types here. Remember, this is untyped lambda calculus. So it's okay for us just to throw around things that are Booleans here, because there's no notion of them actually being Boolean. So remember, true and false are already defined as these operators to select the first or second element. So that's all you have to do to create a first and second function. So there's an example of a little tiny data structure. You could imagine, or ideally, try and design some more advanced data structures. Yeah, can you create a triple with functions for getting the first, second, and third elements? Can you create an array? Can you create a vector, and then all your favorite data structures from the languages that you like to program in? Okay, predecessor function will be used later on, so we're going to have to define it. So we've seen the successor function, which adds 1 to things. Predecessor function subtracts 1 from things. And it's a little harder to do this. I'm not going to go through why this works. I'm going to show it to you, and I'm going to get you to play around with it. And the easiest way to convince yourself that this works is just to actually do it. So, the take-home message is that it exists, and it's more complex than the successor function. And for example, if you apply that to the number 4, there's the p combinator on the 4 combinator, you end up with the number 3. So this is going to be important for things like loops. Okay, when you do a loop, you need to count down. You're saying do something 4 times, then do it 3 times, then do it twice, then do it once, then stop. That's why we're defining a predecessor. Also talking of loops, you're going to have to test the values of numbers. And this should look very like assembly language programming. And we want to say, is a numeral 0? Is it greater than something or less than something? Or is it equal to something? So here we have a Z combinator. Oh, Matthew? Question from Matthew?
Hi, yeah. I understand the need for comparators, but in terms of loop, do we need to be able to express loops if we can express the repeated application of something? Because we've already defined being able to recursively repeat a function. So
yeah, this is a good question, which one of my compilers projects is currently struggling with. There is a big difference between a for loop and a while loop. Okay, if you have a for loop, that's going to run a fixed number of times and it will stop at the end. A while loop can potentially run forever. So a while loop can do something that a for loop can't. Okay,
But couldn't you have something like you could encode like the idea of memoization? So we'll return something that we can look at in a comparator at the start of the function that we're repeatedly applying, and that would be like a while loop, wouldn't it?
I think that's roughly what we're going to do. So yeah, you need the comparator to make a while loop. You wouldn't need this to make a for loop, because a for loop is completely
but would you then do you need the predecessor function then? Oh, well, you're using it in the comparator itself. So if you need to be able to, okay, there we go.
Okay, good. Okay, so testing if a number is 0, you can see this has been formed out of the false and true functions. Here, they're not being used in their Boolean meanings. They're just part of the form of this function. Roughly, this is going to take. We've seen the 0 function. 0 takes 2 arguments, just returns the second one. Doesn't apply the first to it any number of times. So Z is set up to select for that. If it sees that behavior of not iterating the function any times, then it's going to return true because the number is 0, and otherwise it's going to return false. Again, you have to do these with a pencil to get a feel for how they work. Okay, let's test if a number is greater than or equal to another number. And for that, we're going to do some subtraction. We're going to run the predecessor function x times. So this is doing y take away x. And then we're going to ask whether the result is 0 using the 0 function. And we're working with natural numbers here. There's no negative numbers yet. So I think if you keep applying predecessor to 0, it'll just stay at 0, as far as I know. Try that out. Here's an exercise. Then we can construct equality from inequality. Is the easiest way to do it. You can say x equals y if it is both greater than or equal to y and also less than or equal to y. Okay. So here's the g function we just defined, and this is Boolean AND. So if x is both greater than or equal to y, and also y is greater than or equal to x, then they must be equal. And so now you have an equality combinator called E. Okay. So now we can ask 3 different questions about numbers. Is a number 0? Are they greater than or equal? Are they equal? And that's the ingredient that's going to show up when we start to create loops. Any other questions about arithmetic so far before we get on to looping recursion?
I have one thing. So Gödel talks about basically the natural number system we're talking about, the kind of piano kind of addition. What you said about how the interesting definer being not that you can have addition and that you can repeat addition, but that you can encode the idea of repeating addition. Does that apply to any function? So if we're not actually talking about the natural numbers and increasing or decreasing them, but instead talking about any function and being able to encode the idea of being able to repeatedly apply that function, are they equivalent? Because if, for example, we look at something like the lambda calculus, they are in a representational sense like the same thing. So would Gödel's theorem apply to anything that does that, even if it doesn't have the ability to do it for addition multiplication?
It applies to anything that can represent natural numbers and addition and multiplication. So if you can construct those things out of whatever it is you started with, then the theorem will kick in. So, for example, if you've got a way of just iterating things n times, you can view that as representing a natural number. And then if you're able to iterate them on each other, then you've got multiplication. And if you're able to pull out addition in some way, then you've got all the representations that you need. So there doesn't have to be an explicit representation of numbers or arithmetic, but there just has to be the ability to build it or build a model of it out of whatever you've got. Does that make sense? Yeah, it sounds like if you have a system that is able to do any sort of iteration, that can be viewed as encoding numbers for a start. Yeah, if you iterate something 3 times, now you have a representation of the number 3. Okay, are you thinking of a particular system? I mean, could we represent addition?
Sorry, I disconnected before I could reply to you. I did hear everything you said though. So yeah, no, that's exactly what I was getting at. The ability to do this. Yeah, there we go. To be able to recurse on yourself. If you have that power in any sense, then Gödel's incompleteness apply. Okay. Yep.
So here's a good question, which I don't know the answer to. Can you represent arithmetic in the MIU system that we saw? Because we saw some pretty complex strings with 27 letter I's and a bunch of U's. Can you find a way to actually encode arithmetic in the MIU system? Because we ended up using arithmetic to do meta logic on it, but can you encode arithmetic inside the system? I don't actually know. Probably not going to figure that out in the space of a lecture question.
Yeah. Spends 30 seconds thinking about it. It'll work out.
Yeah, good. Okay, so to complete a programming language, we've got our numbers, we've got our basic booleans, if then else. The last thing we need is recursion, roughly equivalent then to while looping. So this is different from just doing something n times, because that gives you something like a for loop. Here you need the ability to say, have we reached the end yet? If so, stop, otherwise keep going. And in particular, that gives you the ability to write programs that run forever, which you can't do just with the numerals or with the for loop. So we've already seen some examples of lambda expressions that don't halt. Okay, so we've been throwing this one around for a while now. Lambda x that returns xx, apply to lambda x that returns xx. So if you haven't already convinced yourself of why this works, try it with the pencil now, and you'll see that this expression evaluates to itself, because this is the argument. It's getting fed in as x, and the act of this function is to make 2 copies of the thing. So it's going to make 2 copies of this, which is the same as what we started with. So here we have a non-terminating lambda expression, and if you put this into your lambda interpreter, unless you're doing something very clever, it will sit there and spin forever. It will keep on evaluating, and it never reaches the end. And that's the flavor of what we're trying to construct to make a while loop, that ability for something to not terminate. So this is not especially interesting by itself because it doesn't do anything. It just sits there spinning. This is the lambda equivalent of 10 go to 10. To make recursion, or to make a while loop, you need to actually do something every time you go around. So what we'd like to do is take a function and a test and spin the function around until the test is met. Yeah, that's what you get in a while loop. And we can do this by constructing this very magical thing called the Y Combinator. Okay, so you may have heard of Y Combinator as a investment firm in Silicon Valley. There's a reason why they're named after this construction in lambda calculus. So you can see the Y Combinator is based upon this endless structure. You can see this part of it has that kind of style to it, but it is also taking a function as an input and it's sticking that function into the computation as it goes. Okay, so this gives you the basic structure of spinning round and round, and in the Y Combinator you're now putting your custom function into the mix that you want to be spun around. And again, if you work this out with a pencil, you will see that the effect of this is to take a small seed as an input. It's going to take your little tiny r as an input, and it is going to amplify it. It's going to evaluate to this. It takes your initial thing and it spits out a new copy there, and then it does it again. It spits out another one, and it's going to amplify your seed to make it bigger and lots of times. And that's the reason why the investment company is called Y Combinator, because R is your startup idea, and they're going to amplify your company and grow it into a enormously profitable IPO. And it's also because the founders of it love lambda calculus, and they love Lisp in particular. Who invented the Y Combinator? As with many of these things, it is controversial. There are two versions of it. As always, one of them is by Alan Turing in 1937, and the other one is debated. It was created by Curry in 1927 in an unpublished letter, and only showed up in a publication in 1950 by Rosser of the Church-Rosser theorem. So take your pick. Turing, you notice here he's doing lambda calculus now, right? This is 1 year after his Turing machine paper. So that's because at this point he'd discovered what Church was doing, and he'd gone over to start his PhD with Church, and he started working on Church's lambda calculus then instead of his Turing machine. So it's one year after the Turing machine when he's studying this stuff with Church. So how do we actually use these things? We have to feed them with a particular choice of R. Okay, so Y is it's called the fixed point combinator, or the Y combinator. Y is a singularly defined entity. Y never changes. It's just describing the process of recursion. But what you're going to do is pick your own R to give it as an input. You're going to give it something that you want to be recursed. And it's entirely your choice what you want to plug in there. Okay, whatever you plug in is going to get recursed like this. And to build a useful program, it's going to have to stop at some point. You don't want this to go on forever. You want some kind of test, like did we get to 0, that says stop. So, for example, consider this little program in a Python-like syntax. Okay, you've probably all written programs like this. This is a program for adding up the first n numbers. Okay, so the sum of 1 is 1, the sum of 2 is 2 plus 1 equals 3, the sum of 3 is 3 plus 2 plus 1 equals 6, and so on. And it is defined recursively here. And you can do it like this. You say if n is 0, then return 0 and stop. That's the halting condition. If n isn't 0, then you return the sum of n plus a recursion on n minus 1. Okay, so the sum of 3, for example, is going to be the number 3 plus the sum of 2. And the sum of 2 is going to recurse to be 2 plus the sum of 1. And the sum of 1 is going to recurse to be 1 plus the sum of 0, which is 0. And then we stop. And so you get the number 6 by adding all of these guys together. So we can encode a function like this using the arithmetic that we've built up so far. Again, try this out with a pencil, try it out with an interpreter. You can see we've got a test for 0, that's the Z combinator. So that's roughly equivalent to this part. Okay, here we're saying, is the number n 0? If it is, return 0 and stop. And otherwise, you return this thing. And this is the equivalent of the actual recursion part. And this thing, you can see here's the number n. That's like this n here that is getting added on to something. And then here you've got a mixture of successors and predecessors. So predecessor of n is giving you this n minus 1 from here. And then you've got r, and that's the recursion. The y combinator is going to suck this whole thing in as big R, and it's going to end up applying it to itself as little r to enable you to go around again. So you can just about translate a recursive function like this by hand to a lambda expression, something like this. Or ideally you would do it mechanically so that you don't have to do it by hand. And that would enable you to use this kind of syntax in your programming language and have it implemented by your lambda calculus interpreter, like the one we saw running earlier. And you can run it like this. So here we've applied the y combinator to our R, and remember R is the thing we wrote, that's our program that we want to recurse. So here we're applying all of that to the number 5, and it's going off and computing the sum of the digits from 1 to 5 for us. So the important thing is that this stops. Yeah, you see the definition of the y combinator, and it goes on forever. Yeah, which is what the investment fund would really like your company to do. But to actually do anything useful, you need it to stop. You need to say, have we got to 0 yet? If so, stop. Otherwise, keep on going around. Or maybe this represents the IPO, right? Have you got to $100 million? If so, sell out and go on holiday for the rest of your life. Okay, so that is pretty much how you build a functional language out of the lambda calculus. We can stop there if you like. Would you like to wait till next week for the MetaLogic and do some workshops? Would you like to look at some MetaLogic for now? Actually, let's look at the MetaLogic now, because we did the looking at the interpreter early on, and also because I set this up with my joke, and I need to recapture the joke. Yeah, there was a point to this. Yeah. Okay. So look, what is meta? Actually, let's do it without the slide. What is meta without looking at the slide? We hear this term thrown around all over the place, right?
Data refers to itself, like in an image photo where it was taken and stuff like that.
Okay, metadata, yeah? So metadata is sitting on an MP3 file or something, yeah? The artist and the year of recording, yeah? So how about terms like meta-learning? Has anyone done meta-learning at Lincoln? I hope you have.
Probably without calling it that.
Yeah, I mean, wouldn't that basically be learning about learning?
Yeah, it's learning how to learn.
Also, problem solving.
Yeah, or it's it's what you do with your personal tutor groups if they're any good. It's what you do when you study mind maps, or you study your own cognitive abilities.
Research methods would be meta learning, I guess.
I don't think I've spoken to my personal tutor in over a year. I just realised.
Get a new personal tutor. We have loads of fun in my group, don't we, Gary?
Absolutely. That's why I've pestered you for 3 years to stay in the group.
Yeah. So look, meta learning is learning to learn. Yeah. So as a lecturer, I also get the fun of meta teaching sometimes. Sometimes I get taught how to teach. So I go and sit in a lecture about how to be a lecturer. And we have many systems at Lincoln. Lincoln is especially into this, by the way. It's a big Lincoln thing, meta learning and meta teaching. You get a lot of meta teaching if you ever study a PGCE. You're going to go and do a degree in how to be a school teacher, for example. Cool book called The Mind for Numbers about meta learning for scientific subjects. Okay, interesting. Yeah, I'd very much recommend meta learning. That's how you really ace your degree and life in general. So, you might come across metafiction. Anyone read any metafiction? What is metafiction? One for David, maybe.
I see. Oh no.
Have
So-
you written any
Writing about
metafiction?
writing.
Yeah.
I don't think I have written any metafiction, but I'm planning to write some metafiction
Mhm.
because for a story thing which I'm currently working on, as part of the world building, I am really tempted to write a fictional Bible, which will then be used as the basis for a religion in that story.
Yeah. So it's an old thing, right? Shakespeare had a play within a play, metafiction. Yeah.
Lord
Good.
of the Rings probably actually would have a bunch of it, considering he spent 50 years writing world building. He almost certainly wrote some metafiction for that as
Yeah,
well.
yeah, and like designing his own language for the elves
Yep.
and stuff.
Gee.
Yeah.
Oh god, he was an absolute madman.
So look, I used to have a friend who was doing meta history. This is the history of history, and this involved digging up parts of ancient Rome to look at museums built by the Romans. Okay, and they were studying how did the Romans do history? Did they understand what all these objects from much older times actually were? How accurate was the history of the Romans? And people do meta history on the Romans now. There's a famous book called The Decline and Fall of the Roman Empire, which was written by a Victorian, and the Victorians were obsessed with the decline and fall of the British Empire. So their whole view of the Roman Empire was coloured by what the British Empire was doing. And so now when people read the book about the decline and fall of the Roman Empire, they're doing meta history to pull out all the parts that were put in there by the British Empire. Meta sociology, right? Why are all sociology professors cisgendered white middle class academics? Yeah, that's the sociology of sociology, which those people can get very excited about sometimes. Yeah. So look, my COVID joke was in fact a fairly high-powered meta joke. I'm going to explain the COVID joke in a little more detail. A more basic meta joke is just any joke about the joke. So, an Irishman, an Englishman, and a Scotsman walk into a bar, and the Irishman says, "What is this? Some sort of joke?" Yeah, that's a meta joke. They're really useful for lecturers as well, because if your main jokes fall over, you can often recover with a meta joke. So I do this one with the first years when my thing about how many types of computer scientists there are sometimes falls flat when we go to the higher version of it, and I have a backup meta joke. Okay, if the joke doesn't work, I'll pull out my pen and I'll do something like, "Oh, student feedback must write better jokes." Yeah, that's a joke about a joke. So in our world of computer science, we see meta in things like meta programming. Okay, programming about programming, writing compilers, writing debuggers. You may have come across the meta language, otherwise known as ML. So ML is a incredibly beautiful functional programming language, which no one actually uses, but it's a very beautiful thing. And it was originally designed as a language for doing meta programming in. So it's called the meta language. It's a language for creating other languages. And look, all of this comes from a somewhat misnamed Greek origin, okay? So ancient Greek meta, they're the same symbols you use in maths, right? That's a mu, it's a meta. In Greek, it simply means something like after or beyond, or maybe above, or post. We like putting post on things in English now. It's a similar idea. What comes after something else? And it comes from an accident. It comes from Aristotle's book, Metaphysics, which was simply the one he wrote after a book called Physics. Right? He wrote Physics, and then he did the book after Physics, and that's the only reason why it was called Metaphysics, the one after Physics. And as it happened, this book was all about ontology, which we've talked about before. And ontology can be viewed as the physics of physics. Physics says what is the world made out of in terms of a physical theory, atoms, superstrings, quarks. Ontology says what is physics made out of? What is a physical theory made out of? And a physical theory is going to be made out of, for example, objects and properties, substances, relations. Modern physical theories might be made out of fields rather than objects, but metaphysics was all about ontology, and as it happened, that was the physics of physics. And so more recently we've taken this meta and we've kind of retrospectively reinterpreted it to mean applying X to X. Okay, so originally this just meant the book after physics, but now it means doing X of X. It means the physics of physics, or the education of education. So we are going to come across this as meta logic. This means doing logic about logic. So we've already seen an example of this with the MIU system. There were some things we could prove within the MIU system. We could derive certain strings as theorems in the system. But if you make a statement such as this system can never find MU, now you're doing meta logic. You're saying something about the system. You're standing outside of it and you're proving stuff about the formal system, usually by using a different logic, a more powerful logic. So for example, we had to use arithmetic to solve the MU problem, when, at least as far as we know, you can't do arithmetic inside the system, unless someone manages to show that for the homework. So you'll also come across meta-mathematics. This is when mathematicians start doing this stuff as well. Those people want to build all of maths out of logic. We tend to use logic for other things, like building programming languages or proving theorems about our programs. For mathematicians, they specialize in applying logic just to building their mathematical entities. And so when they talk about meta-mathematics, they really mean applying logic to mathematics. But if you've built your mathematics out of logic, then you're effectively doing meta-logic again. Meta-mathematics usually reduces to meta-logic. So that COVID joke was actually a higher level than a regular meta joke. That's actually my top quality meta joke. It's like when the NSA pull out their best exploit to put on all the Windows computers. I've been saving it for the. So there is a stronger form of meta, which Hofstadter calls a strange loop. So meta just means using some theory of X to talk about theories of X. Okay, using any logic to talk about other logics, or using a lecture to talk about giving lectures in general. A strange loop for Hofstadter is a particular strong form of this, when you use the actual theory of X to talk about itself, not to talk about other theories of X. So we might consider, say, strange loop education. Okay, meta education is just teaching how to teach, like a PGCE. A strange loop education would be teaching how to teach the course you are actually on. Okay? This is a self-referential lecture that teaches you how to give the same lecture. The only case of that I can think of is pyramid selling seminars. I've been to a couple of these for entertainment, and they'll invite you to a hotel lobby and tell you you're going to make $1 million by doing this thing to 10 other people. And the people giving the talk understand that it's a pyramid scheme, and they understand that you understand that it's a pyramid scheme. But they say all you have to do is go out and give this talk to 10 more people and take $100,000 off each of them, and then that will make you a millionaire. So there you have a stronger form of meta. You have a strange loop in that you're teaching the thing that you're teaching. Again, you'll find this very occasionally in fiction. So this is not just fiction about fiction. It's not like Shakespeare's play within a play. This is fiction which is describing its own creation. It loops around and the story describes how it was written. So you'll find a lot of this in the work of Borges, which is pronounced with a sort of South American H instead of a G, Borges. And occasionally in movies, so Charlie Kaufman is very into meta. I think the only case of him actually reaching strange loop status is in the movie Adaptation, which is a movie all about its own creation. Lots of fun to watch. So yeah, my COVID joke I think is a strange loop joke. It's my top quality meta joke because it actually refers to itself rather than to other jokes. And Hilbert's dream, which didn't work. This is the thing that was destroyed by Gödel's theorem. Hilbert's dream was the idea of using a logic to do meta logic on itself. Okay, when we've done meta logic on the MIU system, we weren't using the MIU system to model the MIU system. We were using another logic with arithmetic in it. Hilbert asked, and this was the real modernist, postmodernist question. Hilbert asked, can mathematics just verify itself? And then we'll all be certain that there is one true maths that exists as objectively as you can. And it was Gödel who showed that this isn't actually possible, that there is no single logic, or there's no single set of rules for doing mathematics, because if you attempt to verify yourself, then there's always something you can't do, and you need to go and make a new logic to be able to do that. So we're not doing strange loops here, we're just doing regular meta logic at this point. Yeah, and in regular meta logic, you're allowed to assume that you have some higher power logic available to do your reasoning in than the logic you're actually reasoning about. So this is relatively tame compared with the strange loop stuff. So when we do meta logic, we're taking a target logic, such as the MIU system or the lambda calculus, and now we're going to look at it purely as a set of symbols and rules. When you work inside the lambda calculus, you're thinking about the meaning of the symbols, what it is that they refer to, like natural numbers or Boolean objects. When we do the meta logic, lambda calculus is now just a bunch of symbols on a page or in a computer, and we're just reasoning about what those symbols are able to end up transforming into or not. So there are two important theorems of meta logic about the lambda calculus. Okay, these are different from the theorems that we show inside the lambda calculus. If we show 2 + 2 = 4 inside the lambda calculus, that's a proof within the system. But now we're coming out of the system, we're looking at lambda calculus from outside, and we're saying, what can we prove about the lambda calculus as we prove stuff about the MIU system. Okay, so the first one is called the Church-Rosser theorem. And this is a very important theorem because when you implement a lambda calculus interpreter, you will almost certainly run very quickly into the question of which beta reduction should I actually apply. You know, there are often cases when there are many options that you could take for reducing a lambda expression. So for example, here's a lambda expression. I'm using the slash for the lambda here, like in an implementation. But there's at least two ways you could go about reducing this. Okay, you could either reduce this chunk first, and that would take you down here. Okay, here you've reduced this to BA, and you've left XXX alone. Or alternatively, you could go this way, and you could leave all this stuff together as a single thing, and you could apply this function to it, which makes two copies of it. So now you've got two copies of the thing on the right. And the magic is that it doesn't matter which route you take, because if you evaluate each of those, you will always end up at the same ultimate result. So this is the Church-Rosser theorem. It says it does not matter what order you do your beta reductions in. You'll always get to the same answer. It's actually a special case of a large class of theorems which are called confluence theorems. So confluence means, you know, this is a river splitting into two, but they always come back and return to a single river at the end. So, you know, there are versions of confluence theorems in everyday arithmetic, right? You know, this is what you do at primary school, probably. You know, how are you going to evaluate this arithmetic expression? Are you going to go and work on this part first, this 11 plus 9, or are you going to go and work on this part? And it doesn't matter, because you can, again, this is a meta-logic theorem. You can prove about arithmetic that it is confluent. You will always end up with the same number at the end. So I can't explain in here why the Church-Rosser theorem works. If you want to see the details, they are here. Somewhat scary. But the important thing to realize is that they are using meta logic. They're not proving it using the lambda calculus itself. Roughly, it's the same story that you get in arithmetic. You could probably convince yourself why this works. And in a similar style, you can convince yourself why it works in lambda calculus. Now, this is important now because our computers are running out of speed. CPUs don't get faster anymore, and so we have to parallelize our computation to get any further speed up. And if your model of computation is based on a serial machine, then you have a big problem trying to do that, trying to figure out how you parallelize anything. If your model of computation is based on lambda calculus, you get this for free. You already get this ability to work on different components of your calculation in parallel, right? So you can have one part of a system can be working on reducing this thing down, and another part can be working on executing this to make two copies, and you can bring them together. And if you have a huge lambda expression, you could have thousands or millions of parts of the computation that will naturally decompose and can parallelize. Okay, it's very hard to do that on a model of computation that is based on just doing one thing at a time. But you get it for free in the lambda calculus because of the Church-Rosser theorem. So yeah, this is also a model of programming language design. You might have come across these concepts of call by value and call by name. Okay, when you implement a programming language, you will often have to decide which of these methods you're going to use. Now, for lambda calculus, it doesn't matter because they both reduce to the same outcome. That's because lambda calculus is a purely functional language. If you have a language with side effects, then this theorem will no longer hold. Now, again, this is why we should all do functional programming, because it's easier to parallelize now. So, for example, if every time you execute this function, if every time you run this application, you make a bang, okay? if you go this way, your system will only output one bang. It'll give the same answer, but it'll only make one bang. If you go this way, you've now got two copies of it, and your system will go bang, bang, and you have a different output. So by including side effects in your language, we can now see that you have to consider whether you're doing call by name or call by value. So this is called call by value because you've evaluated the value of the argument first. Okay, your main function is this one. It's being applied to this thing here. And in call by value, you figure out the value of the argument first. You execute that, you figure out what it's worth, and then you plug it in as the input. In call by name, you just take the name of it. This whole thing is a string, effectively. It's the name of what's getting passed in. And you plug that whole name in. So, you know, here we get some insight into why functional programming is going to be easier to parallelize, and why non-functional languages are going to have to make this distinction. Okay, and then the other big meta-logic theorem of the Lambda calculus is the halting problem, as proved by Church in his 1936 paper, which I've given you guys a copy of. So the halting problem asks, if you're given a program in Lambda calculus and a machine that's going to execute it, will the machine ever halt, or will it get stuck in an infinite loop? Okay, so we've seen examples of Lambda expressions which do not halt. When we looked at the Y combinator, we started with this fairly unpleasant beast that just goes into an infinite loop. And when you create a while loop, effectively, you're taming that recursion and you're making it end because you have a definite endpoint. So, you know, can you take a program like this, all based on Y combinators and these decisions, can you look at that Lambda calculus program and determine whether or not it is going to ever end, or will it go into an infinite loop? And the answer to this is no, which was a huge shock to many people, because the Lambda calculus was created by Church as a model of computation, as a definition of computation. You know, anything that the Lambda calculus can do is computable, or anything that a machine reducible to Lambda calculus can do is computable. And it would have been nice if that definition included being able to do anything. But here we found a task that you cannot write a program to solve. So, look, this is linked to the Church-Rosser idea. Okay, the Church-Rosser theorem shows that if an expression has what is called a normal form, so a normal form is one that you can't apply any more beta reduction to. Yeah? Your Lambda interpreter has stopped when it can't apply any more reduction. So the Church-Rosser theorem shows that if an expression has one of these things, it will always reach it and it will halt. And it doesn't matter what order you do the beta reductions in. So therefore, the halting problem is equivalent to asking, is there an algorithm which tells us if a Lambda expression has a normal form or not? Okay, these are equivalent formulations of the halting problem. Again, there's a full proof in the book. I'm going to give you a sketch of this one because it's actually a weirdly simple idea. Okay, so the halting problem says, can you find an algorithm that says if any expression has a normal form? Okay, and let's assume that there is one. Okay, this bracket means suppose. We're going to enter a possible world for a while and see what happens if we suppose something. And here we're stopping supposing things and coming back to the real world. But suppose for a moment that we have an algorithm It says if any expression has a normal form. And remember, an algorithm is anything that we can encode in lambda calculus, because that's the definition of what lambda calculus is. It's a model of computation. So let's suppose we have a function written in lambda calculus, h, which does this, okay? You're going to feed it with an expression, e, and this could be any lambda expression. And if e has no normal form, it is going to return false. Okay, so look, this is not written in lambda calculus, this is written in English. And the reason for that is that we don't know what the function is, okay, but we're just assuming that one exists. You know, if one did exist, it would probably be quite a complex function with lots of lambda terms. But if it existed, this is what it would do. It's going to take your expression and it's either going to return false or it's going to return true, telling you whether or not E has a normal form, and therefore whether or not E is going to halt. If you had such a function, you can then blow it up as follows. Okay, so consider this expression. This has got many of the things we've seen today. Remember, Q is a question. Q is your if statement. So Q says, is this thing true? If so, do this, otherwise do that. Okay, it's if, then else. And the thing we are going to ask in that question is this. We're going to say, does expression EE halt or not? We've assumed that H exists. That's the halting function. And we're going to feed it with EE. Okay? We've not said what E is yet. E is just whatever is the input. So we're going to replicate it and then feed it into the halting function. If the thing does halt, we are going to do this. And remember, this is an infinite loop. Okay? This is the expression that never halts because it evaluates to itself. It has no normal form. If this thing does not halt, then we are going to halt. Okay, we're just going to return the number 0 and then we're done. So we're given an expression E, we make 2 copies of it and we say, does that thing halt? And if that thing halts, then we don't halt. And if that thing doesn't halt, then we do halt. We do the opposite of whatever EE does. And then we're going to feed it into itself. Okay, this is the magic. We're going to apply this whole function to itself. We're going to give it a copy of itself as an input and apply it to itself. So you can see this now has the form of that EE. So this program is now paradoxical because this is the function being applied. It takes this function as an input, which is a copy of itself, and it says, if I halt, then don't halt. And if I don't halt, then do halt. So it contradicts itself. Okay, if it halts, then it doesn't halt. If it doesn't halt, then it halts. And this is a contradiction, okay? And we are, if you're doing paraconsistent logic, we are now in one of these paradoxical states. This thing is neither true nor false, it is a contradiction. And as we've seen, being in that state means that you have a problem. It means that something was assumed that has made everything go wrong. And the only thing we've assumed is this supposition here. We assumed that a halting function existed. So now when we come out of that supposition, we can now say, therefore, our supposition was impossible, so no H can exist. Okay? So here, Church is showing that there is a problem that no computer can solve. And the problem is the halting problem. Given a program, find out whether or not it's going to hot, and you're going to blow it up through this form of self-reference. You know, you might view this as a type of strange loop, that you're feeding a function with itself as its own input. Lots of lambda calculus. We've got half an hour left if you guys want to meet up and get into groups and chat about some of it. I think we've already seen Matthew's lovely interpreter. You know, we recorded that as well, if you want to study the guts of that in detail. You know, can we maybe take 5 minutes off for another cup of tea if you like, and then let's come back and we'll sit in our groups and just go over a few of these issues. Does anyone have any questions before that?
Sounds good.
Yeah.
That was weirdly, that last slide was weirdly comprehensive. You know, usually the English form of the halting problem, especially Turing's expression of it, running it in English, it makes sense, but that's weirdly. It seems very, very simple for what it is, especially having read Church's paper. A lot of Church's paper is a lot easier to read than a lot of stuff about Church's paper, which I find kind of funny. But he doesn't say anything as simple as that in there. You know, that's wow. Yeah, that's really pretty.
This is my version of it, right? It's about defining this little Q thing. I think is the secret. Is if they know. But yeah, Church's paper is rather longer than this. Yeah, this has been done with the benefit of nearly 100 years of everyone thinking about it to try and make it easy. When Church was doing it, he was making it up as he went along. So yeah, so let's take 5 minutes and then come back, sit in. Let's just have 3 groups, pick a random number from 1 to 3. We do need to start thinking about the assessment now, or this lambda interpreter part of the assessment. You know, you can chat about lambda interpreters. You could try working through some of the examples on these slides by hand. You know, try some of the Church arithmetic, try some Boolean logic. You know, ultimately, you've all got to write your own description of how a lambda interpreter works. You can either talk about one you've written yourself or talk about one that someone else has written. That's what it says on the CRG. Yeah, maybe have a chat about the halting problem. Can you convince yourself that this actually works? As with all my sides, maybe there are some bugs in it. Maybe there are some missing brackets, whatever in it. Have a talk through. So let's have 5 minutes off for a cup of tea. Come back in groups, and I'll catch up with some of your groups then. Okay. See you then.